once again. I started it and then lost it. So this is our first part of our work, power, and energy, and there's actually 3 parts. So this first part is primarily just about your work and power, and you can add this information to your note packet. General definition of work is that it's a scalar quantity equal to the product of displacement, which we would call x, and the component of the force in the direction of the displacement. Now, work is a scalar quantity because of the fact that the displacement and the force have to be in the same plane. So we're not worried about the directional value of it. So it becomes a scalar value since they have to be in the same plane. Now, work, the formula would just be force component multiplied by displacement, which on your formula chart is F cosine theta multiplied by x. Now, work in order for it to be done, 3 things are necessary. 1, there must be an applied force, and 2, it has to be moving, so there has to be a displacement. And 3, the force and the displacement have to be in the same plane with each other. That's what the force must have a component along the displacement. If I look at these 3 examples, the first one here has a force but no displacement, so that would be 0 work. The second one has a force and has a displacement, and they're parallel to each other, so it would be, they're in the same plane, so there would be work equals force times displacement. And this last one, we have a force at an angle, and it's along a horizontal displacement, so there is work, but the work is only on this x component of the force, because that component and the displacement are in the same plane. So we have to make sure we take care of those things. We then can look at the units of work, because I'm a big stickler on your units. And units for this, remembering that force times displacement. So force can be mass times acceleration, which is kilograms meters per second squared, which creates a newton. That was our derived unit. Well, then work can be newtons times meters. So we could call it a newton meter, but we get lucky in the fact that there's a derived unit for a newton meter, and that's a joule. So we can just list work as a capital letter J as the answer for a joule. And in the customary system, it's foot-pounds, but we will always use joules in our class. Now, we can talk about things like positive work and negative work. Positive work would be when the force contributes to the displacement, meaning that the force vector and the displacement vector are in the same direction. So if our example is 40 newtons times 4 meters, then we would come up with a positive work value of 160 newton meters. So that could also be written as 160 joules, remembering, because a newton meter is a joule. Now, if I talk about negative work, notice my frictional vector is to the left, but my displacement vector is to the right. So the force is opposing the displacement, so they're in opposite directions. And so that's what we would consider to be a negative work value, because the force is negative and the displacement is positive. So our negative work would be negative 40 joules. So primarily a thing to remember is if the force and the displacement are in the same direction with their vectors, then it's positive work. If they're in opposite directions, then it is negative work. And then we can talk about it when it's at an angle. And when it's at an angle, we end up with the fact that our displacement vector is on the horizontal, but our force vector is actually at an angle. So what we'll have to do is we'll have to take a component of that force, and only the component that is on the horizontal plane will contribute to the work. So we would have 70 newtons multiplied by the cosine of 60 to get the Fx value, and then we would multiply that by the 12 meters, which would give us 120 joules. So only the x component of the force is doing any work though. So that's something just to remember. Now we can talk about graphing, and if you remember when we talk about graphing, we have to remember that graphs really are just the 2 things that we always look at when we graph is our slopes and our areas. So if we look at the area of this, because this line doesn't have a slope, so if we look at the area of this, we would have force multiplied by change in displacement. So that's really work, because force times change in displacement is work. Alright, so area under a curve on a force versus displacement graph is the work. Alright? So then if I do an example and I look at it this way and I give you numbers and I have 40 newtons as my force, it's constant. I move from 1 to 4, which means I'm moving actually 3 meters. So I could take that 40 newtons, multiply it by 3 meters, and get 120 joules of work. So remember, graphs, things we look at, slope and area. If this had been a triangle and the force had been changing as well, we would just do 1/2 divided by your change in force, or excuse me, 1/2 multiplied by your change in force times your change in displacement. So we could do it that way too. Now, power is the rate at which work is done. And power really is, when you think about it, everything that's a rate is anything just really divided by time. Okay? So if I'm taking it and dividing it by time, then it's the same as saying like speed is the rate at which distance changes. And velocity is the rate at which displacement changes. And acceleration is the rate at which velocity changes. So all of those things are just rates because they're divided by time. So power really is work divided by time. And remember, we can say work is force times displacement divided by time. Units would be joules for work and seconds for time. So we also get another derived unit, which is that joules per second is a watt. So we have joules that are a new unit, we have watts that are a new unit, and in the English system, power is measured in horsepower, which you guys are familiar with if you know anything about engines. So also conversion factor, there's 746 watts in 1 horsepower. So that would be like saying there's 60 seconds in a minute. Okay. So if engineers ran summer camp, things like this would be written for at home. Dear Mom and Dad, Camp School, today we used an energy conservation device to shoot arrows into a target. It was fun. Can I stay another week? Well, it's funky. Alright, we'll do example problems in class tomorrow, and have a good one.